Hello, dear scientists of the future, supportive parents and guardians. Welcome to TIRADPAS Network, DepEd Candon City Teleskwela, kanlungan ng kaalaman tungo sa kahusayan at kaunlaran. Tara na! It's science time! This episode is for Grade 9 Science, Quarter 2, Week 1. I am Teacher Nelda and I'll be your teacher for today's episode. Let us learn science in an easy and fun way. Are you ready to have fun while learning? That's great! Let's get started! This week's episode in Quarter 2 is anchored from our most essential learning competencies, which is to explain how the quantum mechanical model of the atom describes the energies and positions of electrons. In today's episode, you are expected to explain the modern description of the atom, describe how electrons are arranged in the quantum mechanical model of an atom, and discuss the 4 quantum numbers of the atom. Before we discuss the modern description of the atom, let us first have a quick review of the electron configuration of elements. In Grade 8, you've learned that electron configuration is a designation of the most probable distribution of electrons in an atom. What are the rules applied in writing the electron configuration of elements? Correct! Aufbau principle is one of the rules in writing the electron configuration of elements. It states that electrons will successively occupy the available orbitals in order of increasing energy. What else? Very good! Hand's rule of multiplicity is the second rule. It tells us that when electrons enter a sublevel containing more than one orbital, they will spread out over the available orbitals with their spins in the same direction before they pair up with the opposite spin. What about the third rule? Excellent! Electrons occupying the same orbitals must have opposite spins. This is known as the Pauli exclusion principle. Good job! Now let's proceed with the quantum mechanical model of the atom. In 1926, Erwin Schrödinger improved the mathematical treatment of de Broglie on the new quantum theory. He used the Schrödinger wave equation to describe the location and energy of an electron of hydrogen. This paved the way for dealing with subatomic particles known as mechanics or wave mechanics. This led to the modern description of the atom, the quantum mechanical model. The quantum mechanical model views an atom as a cloud of negative charge having a certain geometrical shape called orbitals. It shows how likely an electron could be found in various locations around the nucleus. As you can see in the illustration, the darker the area, the greater is the probability of finding the electron in that area. This model gives information about the energy of the electron. It describes the region of space around the nucleus as consisting of shells, also called principal or main energy levels. The principal energy levels or shells may have one or more sublevels assigned with letters S, P, D, and F. What are quantum numbers? Quantum numbers are a set of numbers used to represent the location of an electron. The number gives the address of an electron in an atom. The 4 quantum numbers are the principal quantum number represented by small letter n, angular quantum number represented by small letter l, magnetic quantum number represented by m sub l, and electron spin represented by m sub s. Let us discuss the principal quantum numbers first. The principal quantum number, denoted by small letter n, can have values 1, 2, 3, and so on. It indicates the size of the orbital and the relative distance from the nucleus. This quantum number also specifies the energy level of electrons. The higher the principal quantum number value, the higher the energy level. Let us take oxygen as an example. Oxygen has an atomic number of 8. Given its electron configuration and orbital diagram, can you identify its principal quantum number? You're right. Its principal quantum number is 2, since the highest numerical coefficient in its electron configuration is 2. Next, we have the angular quantum number. The angular quantum number have values from 0 to n-1 for each value of n. Always remember that small letter n denotes the principal quantum number. The angular quantum number defines the shape of the orbital. If the principal quantum number is equal to 1, angular quantum number will be equal to 0. If the principal quantum number is 2, angular quantum number values are 0 and 1. And if the principal quantum number is equal to 3, the angular quantum number values are 0, 1, and 2. The value of angular quantum number for a particular orbital is designated as S, P, D, and F for sharp, principal, diffuse, and fundamental respectively. These are the spectral lines observed by physicists in energy transitions. Using the same example, let us identify the angular quantum number of oxygen. If your answer is 1, you're correct. It is because the principal quantum number value is 2, and the last electron is found in the p sublevel. Another quantum number is called the magnetic quantum number. It has values of -1 to 0 to +1. This quantum number describes the orientation of the orbital in space. Each sublevel has a different number of orbitals. If the angular quantum number is equal to 0, magnetic quantum number is also equal to 0. If the angular quantum number is equal to 1, magnetic quantum number will have values -1, 0, and +1. Again, we will use oxygen as an example. Looking closely at its orbital diagram, particularly p sublevel, the last electron is found on the first box or orbital. What is its angular number? Great! The angular quantum number is -1. P sublevel has 3 orbitals, px, py, and pz, represented by the 3 boxes. And the first orbital is assigned with a value of -1. The second box is 0, and the third box is +1. Since the last electron of oxygen is found in the first box, the angular quantum number of oxygen is -1. Moving on to the fourth quantum number, the electron spin. This quantum number describes the spinning of electrons on its axis. This was proposed by George Uhlenbeck and Samuel Abraham Goudsmit. There are 2 possibilities for electron spins. A value of +1/2 denoted by an arrow pointing up, or -1/2 denoted by an arrow pointing down. A spinning electron generates magnetic field, but a pair of electrons with opposing spins has no magnetic field. Using oxygen as our example, can you identify its electron spin value? Very good. The last electron is denoted by an arrow pointing down. Hence, the electron spin value is -1/2. We have reached the end of our discussion, and so let's have a wrap up. The distribution of electrons in the different atomic orbitals is called electron configuration. The quantum mechanical model of the atom describes the atom as having a nucleus at the center around which the electrons move. This model describes a region in space where the electron is most likely to be found. Quantum numbers is a set of numbers used to represent the location of an electron in an atom. The four quantum numbers are a principal quantum number, angular quantum number, magnetic quantum number, and lastly, the electron spin. Let us apply what you have learned by having an exercises. Are you ready? Direction. Given their electron configuration and orbital diagram, write the set of quantum numbers of the following elements. Item number 1 is already accomplished for your reference. You are given 2 minutes to answer. 30 seconds for each number. Ready? Your timer starts now. Time is up. Now let's check your answers. Did you get all the answers correctly? If yes, very good. If no, that's okay. We have reached the end of the lesson. I hope you had fun learning the quantum mechanical model of the atom. In our next episode, we will be discussing on the different types of compounds based on their properties. Thank you very much for tuning in. Once again, I am Teacher Nelda saying, enjoy learning science. See you next time!